Okay, everybody. So let's go ahead and get started. What we're going to be doing today is we're going to be looking at section 5.3 again, which was structural induction. And we're going to look at part two, which is an introduction to trees. Now, before we do that, I do want to actually cover one example that we did not cover in the previous lecture that's not on trees. So here's what I want to do. So this is from before. This is just an example. Um, and what I want to do is I want, um, let's see, write the recursive definition or find a recursive definition of polynomials, all polynomials. So the set of polynomials with integer coefficients. All right. So recursive definition of the set of polynomials with integer coefficients. What are those? So you know what polynomials look like, right? They're like, here's a couple examples, like p of x equals, 3x. That's a polynomial. Q of x equals, let's say, negative 5x to the 7 plus 2x plus 4, right? Stuff like that. Those are polynomials. But we want the set of all polynomials with integer coefficients, anything with an integer coefficient. So the powers on x need to go up as high as possible, because you might need like r of x equals you know um 3x to the 1 million or something like that. So we have to accommodate all of these cases here. Positive coefficients, negative coefficients, but only integers. And we need all of them in a recursive definition. And so, the way to think about that is say, okay, well, what's the smallest pieces that we can build polynomials out of, right? And so what I would say is that the smallest pieces you can build a polynomial out of is a constant like this one, right? You need a constant like this one. And the other small thing that you can build a polynomial out of is an x, right? So we're gonna need a constant by itself, like a 4. Doesn't have to be 4, of course. Probably we're gonna use 1, but you're gonna need a constant by itself, uh, because I think polynomials sometimes have a constant, and you're going to need an x because mostly polynomials have an x. But I think we should be able to figure out some way just to build all polynomials just out of a constant and x, I think. So the basic building blocks seem to be seem to be a constant like 1 and an x. That's what I think. Okay. So with that in mind, let's try to write our recursive definition now. So let's say S be the set defined by, we have a basis. What's the basis for the set? Well, like I said, I think that we can build it out of a 1 and out of an x. So let's just say that those are in the set. So 1, that could be an S, and x, that could be an S. So that's my basis for the set. Now, then what we need is the recursive part, where I tell you how to build new things in the set from the old things in the set. So here's what I think about that. So I'm going to write it right there, but I need to scribble a little bit off to the side here. So I think I will, maybe over here on the left. That's not what I wanted. All right. So what are we going to do? Well, think about it this way, right? Like right now, um, all I've got for polynomials is 1 and x. That's it. Well, how am I going to get another polynomial, right? Like how would I get, for example, a 2? 2 is technically a polynomial. How would I get that? In order to get the 2, I'm probably going to have to do like 1 plus 1, right? So we should be able to add these things to get new polynomials, right? Let me get this 2 off, right? If you add the ability to add these, what kinds of things you would get? Well, you would get like 1 plus 1, which is 2. That's a polynomial. You would get 1 plus x. That's a polynomial. 1 plus x is 1 plus x. What else would you get? Well, you would be able to add these 2 new ones to the old ones, and you would still be able to get more. So you'd be able to get, for example, 2 plus 1, which would be 3. That would be a new polynomial. Or you would be able to add another, you could add 1, you could add a 1 to this one again, and you'd be able to get like 1 plus x plus 1, which would be 2 plus x. So that's good. We could add x, so you could add 1 plus x would give you 1 plus 2x. So far, so good. So I think part of my recursive definition should be that if, let's say, a is in S, so a is a polynomial. Actually, maybe I'll change it. We'll call it p. If p is in S, so p is a polynomial, and q is in S, so q is a polynomial, then what kind of stuff needs to be in S? Well, so far, I think p plus q should be in S. That would give me stuff like what I've just written down. But that's not going to give me all of the polynomials. For example, it's not going to even give me, it's not going to give me any kind of negative numbers, is it? Right? If I can only add, I'm never going to get any negative numbers. So maybe I should do subtract. That way I could do 1 minus 1, which would be 0. That's a polynomial. Or 1 minus x, which would be 1 minus x. Or I could do x minus 1, which would be x minus 1, and so on. And so in order to get negatives in there, maybe I should also have p minus q in S. Now, something I could do is I could leave this off. And I could come up here and put -1 in S, and maybe like -x in S. And then I wouldn't need to have subtraction, because adding a negative is the same as subtraction. But, that's just not how I chose to do it, right? The way I'm going to get negatives in is by adding subtraction. So far, so good. Now, the problem with adding and subtracting is that with adding and subtracting only, my x's, I could have an x and an x and a 2x. I could have a negative 2x down here if I allow subtraction, because I could take this and I could add, I could have 0 minus x would be negative x, and then I could add that to the previous, to this one, and have 1 minus x would be 1 minus 2x, for example. So I can get x's, but how am I going to get an x squared? How am I going to get an x cubed? Right? How am I going to do all that? In order to do that, I must need multiplication. Multiplication would allow, if I could multiply things in this set S, I could take the 1 times the x, for example. And of course, that would just give me x. But I could also do the x times an x, which would be x squared. And then I could do x times x squared, which would give me x cubed, right? So I can get all my powers of x if I'm allowed to multiply things. And also, because I can add, once I have an x cubed, I would be able to take the x cubed up and, if I do more adding, I'd be able to do x cubed plus x cubed, and that's how I would be able to get, a 2x cubed that way. So if you combine multiplication and adding, that's how you'd be able to get a coefficient in front of a power of x. But you need multiplication. So up here, I've got addition and subtraction, but I also think I need multiplication. So between all these, I think I can get positive coefficients from adding. I can get negative coefficients if I'm allowed to subtract. And I think I can get powers of x if I'm allowed to multiply them. And with those three operations, I think I can make all polynomials out of, 1 and x. So that's the kind of thing you have to think about in order to do this type of problem. Yeah, so that's it. That is our definition right here. That's not going to be able to make a straight line. So that is our definition. If you start with 1 in x and you're allowed to add, subtract, multiply, and divide things in S to get new things in S, then you should be able to make all integer coefficients. Now, you do have to be careful here, right? Addition, subtraction, multiplication all have to be defined. You could not add division. You could not add division because, first of all, since 0 is in there, if you allowed division, you'd have to worry about divide by 0. And also, if you allowed division, you would have fractions, right? Like, because if you had division, right, you know that you'd have something like, 2x cubed, for example, and you might also have like a 5. And then if you allowed division, you would have 2x cubed over 5, which would be 2/5 x cubed, and that's not allowed, right? That's not allowed because we were specifically trying to make integer coefficients. Now, if you were looking for polynomials that had rational number coefficients, then maybe rational number means fractions, then maybe you would have to allow division and then just do something to disallow a divide by 0. But this is not what we want because we're specifically limiting ourselves to integer coefficients on these polynomials. All right, so that's some stuff there. So I wanted to do that because it's going to be in the homework and you'll have to figure it out. And let's go ahead and move on and get into trees, which is what I said we were going to do for this lecture here. So, all right. So there it is. There's my definition. All right. So trees. Now, the thing about trees is that there are a number of different kinds of trees, right? There's like an oak, and then there's like a sycamore and willow and so forth. And we need to talk about all of them. Not all of them, but a couple of them. So there are different types, and the different types have different definitions. Like what kind of types? So we're going to look at rooted trees. Those are going to have one definition. We're going to have extended binary trees. full binary trees, and that's probably, I think that's it in this section. Right? So each type has its own recursive definition. Slightly different definition. And the differences in the definition actually will, obviously give us what we're going to see as the differences between the different tree types. So yeah, so let's go ahead and get started. So we're going to look at rooted trees first. So I'm going to give you the definition, and then we're going to draw the pictures. Okay, so I know that, if you've seen trees before, you've seen it with a lot of pictures. So here's our definition of a rooted trees. All right, the set of rooted trees. Let's highlight that so you can find it. So the set of rooted trees, okay, I'll write it in words instead of just symbols first, but we're going to write it in symbols. So the set of rooted trees consists of a set of vertices. We'll look at these, what these mean. A set of vertices containing or distinguished containing a special vertex called the root, and edges connecting these vertices. So that's just kind of a little bit about trees in words here. The symbols or the recursive definition, formal definition looks like this. So for your basic step, so a single vertex R is a rooted tree. All right, so we'll draw our pictures down here. I guess we'll actually have to come down to the next page here. So rooted trees. All right, so basis step. What's the smallest rooted tree look like? Well, the smallest rooted tree is this, a single vertex. Vertex is just going to be a dot. Now, then what we're going to do is we're going to be building more rooted trees from this single vertex. How are we going to build a new rooted tree? Well, that's what the inductive step is for. So, I should say not inductive. We're not doing induction, but this is a recursive definition. So I'll say recursive step. All right. What's the recursive step? So this is supposed to tell us how to build a new rooted tree out of an old rooted tree. So suppose you've got some trees already. So T1, T2, up to Tn are disjoint rooted trees. And I'll define this word in a minute. Disjoint rooted trees. Actually, I'll do it now. So disjoint means that they are completely separate, because what you don't want is, like, let's say that this is a rooted tree and this is another rooted tree. Now those are both rooted trees. But what they don't want is for you to say, well, this right here, this is your T1, and then somehow you have your T2 that's actually part of T1. You would not want that. Okay. So you would want the case where the trees are completely separate. So that's all disjoint means, is separate. It actually means nothing in common. So I'll say separate with nothing in common, with no vertices or edges in common. Now, that's not actually what disjoint means, right? Disjoint doesn't apply to trees only, but in this case, that's what we mean by disjoint. So T1, T2 up to Tn are disjoint rooted trees, so they're just some trees. And then what you're going to do is you're going to put them together. So T1 up to Tn are disjoint rooted trees. I put a period, but I shouldn't have. With roots R1, R2, up to Rn, right? So each tree has its own root. We know that that's the case because according to the basis, or sorry, according to what I said before I wrote the definition down, the set of rooted trees consists of I wrote that wrong, didn't I? I wrote the set of rooted trees consists of, but the set of rooted trees where a rooted tree right, that goes right there, consists of a set of vertices containing a special vertex called the root. So every tree has a root, and that's why I know T1 through Tn, there's in trees, there must be in root. Okay, so so we have that many rooted trees. What are we going to do with them? We're going to form a new graph or a new tree. So the new graph consisting of should be a new root R, and an edge from R to each of R1, R2, up to Rn. That's a rooted tree. So the new graph consisting of a new vertex / root, R, and an edge from R to each of R1 through to Rn is a rooted tree. So what's that look like? So what that means is you can take what that means is you can take any number of rooted trees and connect it to a new R. So like if this is your R1 from your T1, actually let me label this T1. If this is where your T1 and that's all there was, then the way you would get a new graph is you add a new R and then you just connect the new R to the R on the graph T1. So there you go. That's a rooted tree. You have a new vertex R, you've got an old T1, you connect R to T1, to the root of T1. Now, we said that you could do this for T1, T2 up to Tn. So it's not just one T1. You could have like a T1 and a T2, right? How would you form a new rooted tree from that? Well, you would have to add a new root, which we'll call R, and then you would have to make an edge from R to both of the other trees. So that's a rooted tree. But then it's not just that, right? You could have a T1, a T2, a T3, and then you could add a new R, and then you would connect R to T1, T2, and T3 with new edges. And that's a rooted tree. And so you can see the pattern, right? That this is just going to keep going on, dot, dot, dot. All right. So that's how you can make new rooted trees from old rooted trees. But then now that you've got a new list of rooted trees, you can make even more. So we can do step 2, get more rooted trees. Okay, so how would we do that? Well, you can pick rooted trees to come from, you can pick your T1 and T2 to come from any of the previous examples. So you could have your T1 now, could be anything. It could be one of these guys, right? For example, and that could be it. So then once you have that, you would just have a new R and then you connect it. So that's a rooted tree. Or you could have just one of these guys, could be your T1. That's a rooted tree. So you have one of those. How would you make a new rooted tree? Well, you add an R and then you connect it. So like that. And so you could continue that for a long time. However, that's not the only kind of thing you could have, right? Because you could have a T1 and a T2. So you could have a T1 where, let's say T1 is just a single vertex, and maybe T2 is one of these guys. Well, then how would you make a rooted tree? You would have a root, and then you add an edge to each of the old roots. So that's a rooted tree. Or, and this is different, and that's why I'm drawing it to make a point here. What if this was your T1 and this was your T2? Then you could have your R there, connected that way. So these two graphs look the same. Like structurally, these are the same, but technically they're different, right? Because here we have this little bit on the right-hand side, and here we have it on the left-hand side. So that's in some sense different, but you can draw it. What else could we do? We could have one of these. That could be your T1, that could be your T2, and then you have one of those. Of course, you can you can keep going, right? Because nobody ever said you could only have two things connected at a time. So you could have dot 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 any number of these. So you could have like a single dot could be your T1. You could have one of these as your T2. You could have another one of those as maybe T3. Maybe T4 is just another single dot. What are we up to? I don't know. 2, 3, 4, 5. Maybe you have one of these as T5. Right? You could have as many of these as you want, T1, T2, T3, T4, T5, and you can always make a new rooted tree by adding a root and then connecting to the other things or the other trees that you're making this one out of. So that's lots and lots and lots of rooted trees that you can make. Okay, so there's no rule kind of like other than having a root and being a tree, there's not really anything that this really that this definition makes you do, right? You could have weird trees like the one that I just drew. And this just keeps on going. And those are rooted trees. So I think you get the idea, right? So you could have you know, step, question mark. Lots of really complicated looking things where you would have, you could have one of these, and then you could have one of these, then you could have one of these. Um, Single dot. You could at some point they just keep getting taller as you get further and further down your step, right? So you can have lots and lots of rooted trees. What they all have in common is they all have a root, and you get them by connecting that root to other rooted trees that you already had, any number of them, and you get a rooted tree. Okay, so that's a rooted tree. Let's talk about other kinds of trees. So let's talk about an extended binary tree. Guess we'll have the definition here. Definition. Why does that get the full word definition? Don't know. It doesn't. That's why. Let's just say extended binary tree. All right. So what's an extended binary tree? These are defined recursively. With these steps. So of course, just like before, we're going to have a basis. I'll call it step. Basis step. What's that? A little bit different than previously. We're going to say the empty set. So nothing is an extended binary tree. And then we're going to have a recursive step. What's the recursive step? So for a binary tree, binary probably makes you think of, the word two. So we're going to do basically what we did in the previous step, but instead of allowing n trees, we're only going to allow two trees. So if T1 and T2 have to have two, are disjoint extended binary trees. Then a new binary tree, I'll say new tree. Denoted, it has a notation for it. Denoted T1 dot T2. So there's only going to be one way to get this. So T1 dot T2 is going to be a specific binary tree consisting of a root R. That's going to be new, a new root R, together with edges connecting R to the roots of T1 and TR, Tn, T2, T1 and T2. Okay. When these trees are non-empty. So you can't add an edge to the root if there is no root because it's an empty graph. All right. So this is similar to the previous definition, but you can hopefully see that it is a little bit different, right? Like allowing the empty set to be a binary tree makes it a little bit different. And because of that, there might not actually be a there might not actually be an edge connecting one of the trees to the new root. So let's draw some pictures. Basis. So what's the simplest extended binary tree? Nothing. Okay. What do the step one binary trees look like? Well, let's follow the definition. Or all right. So we need T1 and T2 to be disjoint extended binary trees. Now, the only binary tree we have so far is nothing. So if you have nothing, so here's T1, and then you have another nothing, so here's T2, like right here it is, here's T2. Then a new tree denoted T1, T2, consisting of a root R with edges connecting R to the roots of T1 and T2 if they're not empty. So you need a new root that we're calling R, and then you connect that root to the previous T1 and T2s. Well, there aren't any, like they're empty sets. So you make those edges, but those edges don't actually exist. So you've got, here's your root, here's your T1, here's your T2, so there's nothing. So it's just R, right? There's your step one extended binary tree. But now that you've got that, we actually have something to build new binary trees out of. So now the step two binary trees, what they would look like is, well, we've got a few different choices now. We could have T1 be nothing, and then T2 could be a dot, right? Or we could have T1 be a dot and T2 be nothing. Or we could have T1 and T2 both be a dot. Now you wouldn't have them both blank, because if they were both blank, you're just going to get this one again. So you have to have at least one dot here. So those are what you would start with. And then to make the tree, you would add the new R, and then you would connect that R to the previous roots, if there are any. So here there is. Why did you do that? Connect. Okay. Here, you add a new root, and then you add an edge. Here, you add a root, and then you add an edge to each. So these are the step two binary trees. Okay. Then you could have step three binary trees. Oops. So the step three binary trees now allow you to choose any of the previous binary trees to be your T1 and your T2. So you could have, for example, you could have, this could be your T1, this could be your T2. You could have, and this is going to be a little bit weird maybe, but this could be your T1 and this could be your T2. So the difference between this and the previous one is that this one goes right and this one goes left. So this one goes left, this one goes right. You could have, one of these. You could have a left, left. You could have a left, right. You could have a single dot, right? You could have a single dot, left. You could have a double and right, and so on. Lots and lots of ways to do this. And then when you make binary trees out of them, you would add a root and then connect. A root and then connect. A root and then connect. A root, then connect. Root, connect. Root, then connect. Root, then connect. All right, and so on. You could have an empty set for one of them. So you could have one of these and then nothing for the other R. So then that would mean that your tree looks like that. And so on. This keeps going, right? There's quite a few here. I think you can write them all down. I think the book does, but looks like they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I think they have 21 of them. And so we're not even half done writing them. I think we're not going to. But there you go. So these are binary trees. So they're called binary trees because each one has, like, here's an example. Each one has 2 branches from each vertex, right? So from the root, 2 branches. Or it has, 2 or 1 or 0. So like this has 2 branches. This has 0 branches. This has 1. This one has 2. This one has 2. This one has 1. This has 0. This has 0. This has 0. Right? This one has 1. This one has 2. So they all, they're binary trees because each vertex can branch into 2 more lower level, basically, like 1 or 2 as you go down the tree. Okay. Now that is an extended binary tree. Let us look at one last kind. So the last kind is going to be actually more simple than this extended binary tree. We're going to have full binary trees. So what is a full binary tree? So it's actually very similar to the previous definition, but what we're trying to leave out is we don't want any blank spaces. Like, why is this half of the tree empty, right? So the way you do that is you basically, first of all, we're not going to allow the empty set anymore. So our definition for a full binary tree is going to have a basis step of a vertex. A single vertex is a binary tree. Single vertex R is a full binary tree. Whoa, why did my pen stop working? All right. And then how do you get a new full binary tree? So if T1 and T2, again, are disjoint full binary trees, then there is a full binary tree T1 dot T2 again. That's how we're going to call it. Consisting of R together with edges connecting the root to each of the left subtree and the right subtree. Oh, so we're calling them left and right subtree now. Did we in the previous? Yeah, they did, but I didn't. Consisting of a root R and edges connecting R, I'll say from R, to the roots, say the root of the left subtree T1 and the left subtree T2. All right. So how is this different than the previous binary tree? Well, let's look. So you have your basis step or your basis full binary tree, and it's just a single vertex. So that's already different, right? Because our basis step here was nothing. And then our step 1 full binary trees is going to be this. So you have to pick T1 and T2. T1 and T2 have to be full binary trees. So you have to pick a single vertex to be your T1 and a single vertex to be your T2 because you have no other choices and you have to have a tree for T1 and a tree for T2. And then the way you come up with the new tree is you have a root R and you connect them. So that's what the step 1 full binary tree looks like. What do the step 2 full binary trees look like? Well, again, you can pick a left and a right subtree. So the T1, T2, you pick. So you could have a single dot for your left, and you could have, well, you wouldn't do a single dot for your right, because if you did, you would just get this subtree or this tree, which is the same one that you already had. So that's why I'm not drawing that. So you could have this for your T2, or you could put that guy on the left and you could put a single dot on the right. Or you could go 2 of these. And I think that's it for choices for T1 and T2. So then how would you make the subtree, or how would you make the new trees? Root, connect the lines. Root, right, R, connect the lines. Connect the dots. All right. So those are your step 2 full binary trees. So notice when I say full binary tree, I don't mean like, this side has to be the same size as this side, not full in that sense. It's full in the sense that from each vertex going down, you either have two lines, or you have nothing, right? Two, nothing, two, nothing, right? Whereas up here on the extended binary trees, you could have 2, 1 from here, 1 down, 1 down. And that's not allowed on the full binary trees. And that's the difference. And that's the difference. So, like, for example, so if I draw a couple trees here, here's a couple of trees. This one right here would be an extended binary tree, but would not be a full binary tree. So this one's extended, but not full binary tree. And why is it not a full binary tree? It's because right here, that doesn't branch down into 2. So that means that, where did this part come from? You couldn't make it with the previous definition, because the previous definition would have required there to be a right subtree, and there was no right subtree there. So that's extended but not full. Whereas this one is going to be a full binary tree, because there's no place where it always branches down into 2. So 2, 2, 2, none, 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 none. There's nowhere where it goes down in one direction, but not there's no part where you have a vertex going to a left subtree, but no right subtree. There's always a left and right subtree, or there's nothing. And that's the difference. Okay, so that's some kinds of trees. We will do some more proofs about them, but we'll do it in the next lecture. Let me stop this recording.